All right, so continuing on with chapter 6. So getting back to how we experience a coherent world. The process that we use to describe the way that we connect all of the different features that we perceive in order to form coherent objects is called binding. Okay? So, for example, here's my cell phone, right? And you see several features of this object. You see the straight edges, you see the right angles here. You see that it is black. You see that this surface is shiny. There's a lot of different things you can note about this object, and we perceive this as a whole object. Now, we already know that inside of our brains, as we've learned earlier, inside of our cortex, we have these feature detectors that detect things like edges and right angles and whatnot. So we know inside our brain that the objects that we see are broken up for analysis, so that we can understand what we're looking at. But the problem with that is, how does it all get brought back together? How does it all come back together to form this unified object that we perceive in our mind's eye as a cell phone? Right? How does that work? So here we have this example here of this person with this brain sticking out of his head. And what this person is doing is looking at a rolling ball, right? And this person is perceiving many different things at once, perceiving how the ball is changing location moment by moment, the color of the ball, the direction of the ball, how fast the ball is going, the depth, the way the ball sounds as it's rolling against the surface that will tell him what the ball is made of. There's a lot of different things, a lot of separate things that are being analyzed, yet it all gets brought together somehow as the perception of a ball rolling on a surface. One of the theories that's been proposed to describe or to understand binding is that of the feature integration theory. Now, feature integration theory is covered in your book. Let's see, let me find it real quick. Let's see. Right here, feature integration theory starts on page 143. Okay. Now we know that objects are analyzed and broken up. We know that they are analyzed into different features. And according to feature integration theory, this takes place during the pre-attentive stage. In other words, before the object is brought into our attentional focus, before it's brought into attention, there's a lot of analysis that goes on of that object. The features of the object are analyzed, broken down, and uh, are going to be used for the later stage. The later stage, after the information has been analyzed, after the information has been analyzed, say from your visual system, we then have the focused attention stage. And this is where all of the features, while you're focusing your attention, all of the features are bound into some sort of coherent perception of what you're looking at. And this visual from your book on page 143 is a nice little, very simple way to hold this theory in your head. So it's very simple, just two separate processes that are described at a very high level here. An object is presented. Prior to you paying attention to it, the object is analyzed. The features are broken down and separated. Once you focus your attention on the object, the features are combined into a coherent object, and that is the point at which perception occurs. There's a lot of not a lot, but there's a lot of interesting evidence, a lot of interesting findings that support feature integration theory. One of them is the illusory conjunctions. We do have a way. I mean, we do mix up features that should be associated with one object, incorrectly associating with another. So, in other words, it's possible for us to pre-attentively identify features from a set of objects, and then when we focus our attention to accidentally grab some features of other objects that weren't there and include them in our perception. So it seems like when we're perceiving things, we break them up into features. Then when it's time to pay attention to them, we gather up all those features and bring them together into a coherent object. And we have done experiments where mistakes seem to be made in that process. For example, the experiment by Treisman and Schmidt. So basically, what they did, they had a stimulus that was presented as four shapes, and here's the shapes. Right here's an example of one of the stimuli that they used, and the shape was flanked by two numbers. In this example, the number would be 1 and 8. Okay. So this display flashed very briefly, followed by a mask, which is a random pattern that is meant to mask out the image that you just saw, so that you only saw it for let's see, 1/5 of a second, according to your textbook. The task was to report the numbers first, followed by the shapes at the four locations. Right, so you had this flashed at you really super quick for just a fifth of a second. A fifth of a second. And then your task was to say, okay, what were the numbers and the shapes that were at the four locations, right? Now notice these shapes have different features, right? It's triangle. So we have, they vary along 3 dimensions, right? You have color. So here's red, blue, yellow, and green. You have shape. So a triangle, triangle, circle, circle. And you have size. Little, big, big, little. Okay, so these shapes all vary on 3 dimensions. So the theory goes, as you're looking at this very quickly, you're very quickly breaking this down into its constituent components, right? So as you're processing this very quickly, you're breaking this into big yellow circle, small red triangle, large blue triangle, or hollow, I guess. I guess the fourth dimension would be open or closed, right? Whether it's an open triangle or a closed triangle. And this would be a small open green circle, right? So you have those 4 dimensions that you're breaking things down to. And the task was to report what you did. Well, if you think about it, you've got these dimensions here, and according to the pre-attentive stage of the feature integration theory, you're going to be breaking up these features into their constituent components. So this thing is going to be broken up into 3 separate features. This is, yellow, big, and round, right? Large. And sure enough, when we ask people in this task, when we ask people to recall what they saw shape-wise, they mix features up. Right. So instead of saying, for example, uh, large yellow circle, they might say uh, small yellow triangle, for example. They'll get the yellows mixed up, okay? It's about 18% of the time that this happens, right? That features get jumbled up with each other about 18% of the time. When we ask the observers to focus on the target, in other words, to focus their attention not on those numbers, right, but on the actual images, the effect goes away. So, in other words, the pre-attention is no longer there, right? You're focusing your attention right away on those objects. There's none of this pre-attentive, looking at the numbers and the objects get thrown into your pre-attention thing, and then when you pay attention to them, you mix them up. That doesn't happen anymore, right? We see this also with certain types of brain damage. So there's a syndrome called Balint's syndrome, where patients with parietal lobe damage show a lack of focused attention and they combine features, so they'll get like so if they're looking at a blue car and a red dress, they'll get the blue. They'll say a red car and a blue dress, for example, right? They consistently do this, and you'll notice that whenever the other thing you should note about this syndrome is whenever you have damage to the parietal lobe, it's gonna, and it depends on what part of the parietal lobe is damaged, usually by a stroke. But the parietal lobe damage almost always ends up causing the type of brain damage where people have trouble mapping things in space, whether it's features or whether it's objects or whether it's people. Different types of parietal lobe damage cause people to mismap different things in their space in their mind's eye, right? So for example, here, let's see, this is from page 628 on 144, right? Um, let's see. Oh, yeah, so this is really interesting, right? So if we just show people random stuff like these, again, you can get this effect if you show these people these three objects, right? You see, a triangle or a cone, right? However you want to call it, right? A oval circle that's blue and a dot, a open circle, right? And of course, you'll get the features mixed up, right? There's like you might end up with the oval that's orange, the triangle that's black, etc. However, if you tell people that instead of looking, at a triangle, a oval, and a circle, they're looking at a carrot, a lake, and a donut. This completely eliminates this effect of mixing up features. Now, why is that? Well, because there's top-down processing involved. We are using the semantic concept of a carrot, of a lake, and of a donut to organize these features into coherent objects. So since they're already organized into coherent objects, there's no need for us to break down the defining features, right? We just look at this thing here and we say, oh, that's a carrot, right? That looks like, and that's a lake, and this is a donut, right? I don't have to worry about remembering that it's a triangle that's upside down and orange and an oval that's blue, right? I just have to remember triangle, lake, and donut, which tells us a lot about how top-down processing works. It tells us that we use these semantic language categories to group things that we perceive. One of the other things that we do, of course, on a day-to-day basis are what we refer to as conjunction searches, and this is where we find a target with two or more features. So, rather than looking for a circle or a square, we're looking for a blue small circle, etc., etc., right? These things that are combined features, right? Um, Once again, we see that patients with parietal lobe damage don't perform conjunction searches well. In other words, if you were to ask a parietal lobe patient to go and search for a moving blue car, right, they would have a really tough time finding a moving blue car, right, as opposed to just finding a car or a blue car, right? I mean, or a blue object of some kind, right? Um, and again, as I mentioned earlier, parietal lobe damage is generally associated with this type of deficit, and because the parietal lobe is the target for the where stream. So remember, we had the what and the how. We had the how and the where streams. One of the streams told you what you do with an object. The other stream of information that flows from your occipital lobe tells you where it's located, right? And the parietal lobe analyzes the information from the where stream. In other words, analyzes the information that's associated with where that object is in space and where that object is relative to you. Okay. So for example, here I can do a very simple search. I can say find the horizontal line. That's pretty simple, right? But if I then ask you to find, then, and this is pretty simple too, right? I can say find horizontal lines. Well, I can say find horizontal lines that are red, or find horizontal lines that are green, I should say, right? Uh, this horizontal green line is very easy to find because it's basically one feature that's different. But this horizontal green line is much more difficult to find, right? Because we're having to sort among two different types of dimensions. We're sorting across the orientation of the line and the color of the line, right? So hunting for this horizontal green line is going to be much more difficult in this sea of complexity compared to this hunt here. Autism, right? Autism has been very interesting for a lot of researchers for many years because one of the cardinal traits of people that are diagnosed with autism is that they would withdraw from people. They do not want to interact with people, and when they do, it's apparent that it is generally a very aversive process for them, right? um so you can actually take autistic people and give them a hypothetical situation about social interaction. So you could say, if Mary says hello to you, what are you supposed to say to Mary? And the autistic person will say, you're supposed to say hello back and how she's doing. You can do that with an autistic people, and a lot of them will perform well, but when they're actually in the situation themselves doing it, they can't do it, right? um, so, one of the possible mechanisms for why this seems to be the case is that maybe autistic people have trouble focusing their attention on the thing they're supposed to be paying attention to, namely a person, right? Maybe they can't separate the person from the background noise. So, Klin and their group did an experiment where they used eye tracking software to determine where autistic people were looking I think the stimulus they used were movies, right? And they were watching what autistic people paid attention to in movies versus what non-autistic people paid attention to in movies, right? And what they found was pretty interesting, right? Whenever we're watching a movie, right, people who are not autistic focus on very specific things in a particular scene. And of course, directors know this, movie directors know this, and they frame shots so that a good movie director will frame a shot properly so that your attention is focused on the right thing. So here we have an example here of this scene between this man and this woman, and apparently this dude's looking at something that's scaring him, right? And that's leading to the plot. And if a non-autistic person is going to look at this and is going to focus right here, right? Because this is where the attention is in this particular shot, because we're observing the reactions of this actor to whatever is happening in the plot. An autistic person, however, they're going to be looking just randomly, right? They're just going to be looking at things randomly and not really paying attention to the thing that they should be paying attention to, right? Again, we have a viewer, a person that is not autistic is looking. So this actor is looking at this picture and pointing at the picture while having a conversation with this dude, right? And of course, um, here we have a person without autism is going to be looking at the actor, looking at the picture, looking at the reaction of this other actor, and then looking at this other what this actor's doing. A person with autism is going to have a really tough time integrating their attention across these things. They start off looking at the actor, but then they sort of float around. Oh, Lee, gee, what's this? Oh, what's this? And they never look at this guy. So right there, it tells you they've got this fundamental inability to process at a very basic attentional level to process social interactions, right? Another example by Pelfrey was where he actually measured responses in the superior temporal sulcus, okay, and looked at autistic and non-autistic participants watching an animated character that moved their eyes toward a checkerboard which it would what he called a congruent condition. So the checkerboard appears, and the character moves their eyes, and they watched another character that moved their eyes away from the checkerboard. So the checkerboard appeared, but the character looked away, right? Um, and the observers, the dependent variable was the time it took for observers to press a button to say that they saw the character's eyes move, right? Everybody was very accurate, right? In other words, so just by watching how long it took, they were pretty accurate. But the activation of the superior temporal sulcus for non-autistic people was higher in the incongruent situation. Right. So in other words, we have in our brains, if you're non-autistic, you have in your brains the ability to separate out what's part of a social interaction, what's not part of a social interaction. The autistic people had equal activation for both. So even though this animated character was looking, let me see if I have it. Yeah, here it is right here. So even though the animated character was actually not looking at the checkerboard pattern in both of these instances, right? This character here is looking at the checkerboard pattern. In this instance, the character is not looking at the checkerboard pattern because it's down here. Um, the autistic person's brain responded the same to both of these things. In other words, they weren't able to tell where this individual was focusing their attention. They have the basic inability to not be able to understand, comprehend where an individual is looking, and in that way we really can't interact with people if we have a fundamental inability to see things from their perspective, right? Um, Another aspect of attention is perceptual completion. This is something we do all the time, right? Obviously, if we have a cell phone and I cover half the cell phone didn't disappear. We were able to complete that. One of the ways that we can measure perceptual completion in infants is through the study of habituation. Habituation occurs when you have been exposed to a stimulus for a long period of time and you quit paying attention to it. That's habituation. It's a form of learning when you've seen something and you've gotten used to it and you don't pay attention to it anymore. Dishabituation happens when you change the stimulus. If you change the stimulus, all of a sudden you'll pay attention to it. And we can measure habituation and dishabituation in babies. So, for example, if we show babies a stimulus, they'll spend a lot of time looking at it at first, but then it'll get boring and they'll stop looking at it. If we change that stimulus, they'll start looking at it again and get interested in it. Or if we don't change it, it'll just continue being the same old stimulus. So, for example, in this example here, what we're doing is we are habituating the baby to this rod movement. So the rod is going back and forth, but it's hidden behind a brick, right? So it's going back and forth, back and forth, back and forth. Then what we do, after we've done this and the baby has habituated to this, then we show the baby either this or we show the baby this. Now, if the baby is surprised to see one of these things, it means that it's new to them. Okay? So if the baby is surprised to see this, that would mean that while they were habituating to this object here, they assumed it was a continuous rod. If, however, the baby is surprised by seeing a continuous rod, it would mean that while they were looking at this, they perceived it as two separate rods. And sure enough, we have data of babies that perceived the rod as continuing behind the occluder and babies that did not perceive the rod. So we were able to track these babies' vision, and by using this dishabituation technique, we were able to separate out the babies who perceived the rod as a continuous rod versus the babies that perceive the rod as two separate rods. They were one group or the other. And if we track the eyes of each of these two different groups of babies, we find that their eyes are behaving differently. So the babies that perceive the rod as continuing behind the occluder, right, we're looking at up here and up here. They were looking at the two ends of the rods. The babies who perceived the rod as two separate objects were focused entirely here in the middle. So they were only focused here on this, basically on the brick, on the occluder.